Alright, now let's see a few examples of GSO process and how we can obtain the basis functions out of the given signaling set. In this example, we have four possible signal types, that is capital M is equivalent to 4. Let me use a highlighter. M is equivalent to capital 4 means you have four possible signal types here: S0 of t, S1 of t, S2 of t, and S3 of t. All these four signals are different than each other. Assume the transmitter has these four possible digital signals that could have been sent at one simple time period from the transmitter end to the receiver end, right? But we would like to minimize their representation. That is, we would like to use a reduced number of signals to represent these four possible signals. So we are going to find out those reduced number of signals using the GSO process, and as a result we would be representing these signals S1 of t, S0 of t, S2 of t, and S3 of t in terms of those reduced signal set that we call the basis functions. So let's see how we proceed regarding this. In the first step, like we discussed earlier, that we can choose any function out of the available set. Let's suppose we have chosen S2 of t as one of the signal in the first step, and we have computed the energy of S2 of t in the second step here, which comes out to be 4, and we have chosen the first basis function phi naught of t as S2 of t divided by the norm of the signal S2 of t. That is S2 of t divided by the under root of E2. The norm of S2 of t is nothing but the under root of the energy. How do you compute the energy of signal S2 of t? You just substitute the signal S2 of t into the energy formula and take the square of the signal S2 of t, integrate over the orthogonality period 0 till 1. So S2 of t is nothing but this signal there, which is equivalent to amplitude 2 for time period till 0.5 and amplitude minus 2 for the time period from 0.5 till 1. So we are going to solve here the energy first, which is computed in this step here, and the answer comes out to be 4. If you solve the integral, the answer will come out to be 4. We compute the norm of the energy, which is under root of 4 equivalent to 2, and substitute it back into this formula there. This is done in this step here. Okay. As you can see now, the first basis function phi naught of t is nothing but S2 of t divided by 2, and you can plot the function. S2 of t was represented here. If you divide the whole function by the constant value 2, the amplitudes will get reduced by the constant value 2, and the function is then represented here. The resultant function is represented here. Now this is your first basis function out of the GSO process and its representation in time domain. Now we head towards the second step, which is choosing another function out of the available sets that have not been tested before. Now we have the option of choosing S0 of t, S1 of t, and S3 of t in the second step. We can't choose S0 of t because it is equivalent to 0. Like I said earlier, as a rule states, we can't choose a function which is equivalent to 0. So we go for the other two possibilities. We can either choose S3 of t in the second step or S1 of t in the second step. We have chosen S1 of t in the second step. So S1 of t chosen in the second step is placed here, and out of it we are going to subtract the contribution or the projection of S1 of t onto the previously calculated basis function in this step. So this is how you do it. The term in bracket is the contribution projected using the previously calculated basis function phi naught of t. So you need to solve this integral here, s1 of t multiplied by phi naught of t integrated over the time period 0 till 1. You see the f1 of t was amplitude 2 for duration 0 till 1, and it is being multiplied with phi naught of t, and phi naught of t is having this alternative amplitudes for the two different times, 1 and -1 respectively. So if you multiply these two functions together point by point, you end up getting this function itself. Since this function is getting multiplied with 2, the shape will remain the same, but the amplitudes will change to 2 and -2 respectively for the two time slots, 0 till 0.5 and 0.5 till 1 respectively. So for 0 till 0.5 you have amplitude 2, and 0.5 till 1 you have amplitude -2 as a result of the multiplication. So you solve this and end up getting something like this. G1 of t is equivalent to S1 of t. And in the next step, you have to normalize this result by its energy. So normalizing the function G1 of t, whether it's the energy, is done in the second step here. You can compute the energy of G1 of t in this step here, and it is computed using the same energy formula. G1 is the energy of the signal G1 of t, which is equivalent to taking the integral of the squared term of G1 of t, which is nothing but S1 of t square, and S1 of t was this signal there. So if you square it, it will become 4. So the second basis function, which is phi1 of t, is nothing but G1 of t divided by the norm of G1 of t, which is here done in this step. And you can easily plot this result as well. You see, phi1 of t is nothing but G1 of t divided by 2, and G1 of t is represented here. You see, and if you divide it by 2, you end up getting the same shape but amplitude reduced to 1, right? So all these steps are self-explanatory, by the way, but I am trying to explain each and every step for you so that you can better understand everything. So we have obtained the second basis function in the second step. Now let's go for the third step, since the rule states that we have to repeat until we have tested all the signals. We have tested this one in the first step, we have tested that one, selected that one in the second step, and now we are left with this one in the third step. So in the third step, we are going to choose S3 of t here, and we are going to subtract the projections of S3 of t onto other basis functions that are previously calculated. That is the two basis functions phi naught of t and phi1 of t. Here phi naught of t and phi1 of t. So we are going to subtract the projection of S3 of t that is there using the basis functions phi naught of t and phi1 of t in the previously calculated steps. And we are going to subtract these projections from S3 of t. In doing so, we end up getting the result 0. Like I said, if the result comes out to be 0, we are going to stop our and if there are no other signals remain, we are going to stop our GSO process. So in the end, we end up reducing the possible signals to 2 only, that is phi naught of t and phi1 of t. Phi naught of t is equivalent to 1 over under root E2 times S2 of t, and phi1 of t is equivalent to S1 of t divided by 2. Since G1 of t was equivalent to S1 of t, so phi1 of t is equivalent to S1 of t divided by 2. Here it is summarized. All right. So the signal space dimension becomes 2. There is, we have only two orthogonal basis function as a result of this GSO process. The dimension of this signal space is 2. The dimension depends on the number of basis functions present in the signal space. So we have only two signals there in the signal space. That's why our dimension is 2. Alright, so this means in the constellation diagram we will have two axes, one for phi 1 and one for phi 0. We can also represent the four signals there as 0 of t, as 1 of t, as 2 of t, and as 3 of t in terms of the basis functions. S 0 of t is equivalent to 0 times phi 0 of t plus 0 times phi 1 of t. You can see S 0 of t is having no contribution at all with all of the basis functions that were calculated. S1 of t is here, S1 of t. This is nothing but 2 times phi 1 of t plus 0 times phi 0 of t. In the next example, I will tell you how did I come up with these in a more formal way. This example was very simple, and I can easily, by just looking at the basis functions and the signals representations, I can compute the contributions. You can see the shape of the basis functions phi 1 of t and phi 0 of t and original signals. You see, if I would want you to represent S2 of t, what would you do? You just look at the shapes. S2 of t is almost similar to phi 0 of t, with the only difference in the amplitudes. Here the amplitudes are 2 and minus 2. Here the amplitudes are 1 and minus 1. S2 of t has nothing to do with this shape, right? So S2 of t is written as 2 times phi 0 of t. And likewise, I have represented other signals as well. Now, using the basis functions represented on a constellation diagram, I can plot these constellation points, signal points. S0 of t has 0 times phi 0 of t and 0 times phi 1 of t, and represented here in the origin. S1 of t is 2 times phi 1 of t, which is here, and 0 times phi 0 of t, that is 0 contribution from the basis function phi 0. Similarly, S3 of t has 1 times phi 0 and 1 times phi 1. So this is now the complete representation of my signals onto the signal constellation diagram using basis functions. Now I don't need 4 signals at the match filter. In other words, I don't need 4 branches of the match filter at the receiver end. All I need is the 2 branches of match filter at the receiver end. One would be matching to phi 0 of t and one would be matching to phi 1 of t. Now, depending upon the contributions that I would receive onto the 2 branches at the receiver end, I would decide at the receiver end that which transmitted signal was sent from the transmitted end, right? So I have reduced the complexity of receiver by 2 times in this particular example. In the next example, I will tell you how to formally obtain the representation out of some mathematical formula, and it's very simple to get it actually. Alright, now this is another example of a GSO process in which we are given with 4 signals again, 4 different signals having different shapes and durations. The time period is assumed to be 3 seconds. That is, the symbol duration is 3 seconds. This signal exists only for 1 second, and it remains quiet for 1 till the remaining time till 3 seconds. Similarly, this signal S3 of t is amplitude 2 till time 2 seconds, and it remains quiet, or in other words sends nothing from 2 till time 3. This signal is constant 2 from time 0 till 3, and this signal is something like this. So the symbol time is 3 seconds for all of these possible symbols, and the transmitter has chosen these 4 possible types to be sent from the transmitter end. But we would like to reduce this representation, and we would like to come up with the basis functions, reduced number of basis functions, at least less than 4, so that we can represent all these 4 signals using those reduced number of basis functions, and the receiver's complexity could be reduced as a result. Right, so let's see how we can come up with the basis function using the GSO process again. And as a first step, we are going to choose one of the signal arbitrarily from these 4 possible signals. We have chosen S0 of t as the first signal in the first step. The first basis function is nothing but the normalized version of S0 of t. That is S0 of t divided by under root of energy of S0 of t, which is E0. Energy can be easily computed using this formula there, and here it is computed as 4, I guess 4, no, actually 12, and under root of E0 is under root of 12, which is going to be substituted there. So first basis function is phi naught of t, which is equivalent to S naught of t divided by under root 12. S naught of t is represented here, and all you have to do is to divide the amplitudes point by point by under root 12. Here it is represented for you. So now first basis function is mathematically represented here and graphically represented there. Now we go for the second step. In the second step we choose another function arbitrarily out of the remaining possibilities. These 3 were remaining, right? So we have chosen S1 of t as the second function here, and out of it we are going to subtract the contribution of S1 of t onto the previously calculated basis function phi naught of t. So the step is solved here in this equation, and we are in the next step we are going to substitute the values of the functions. S1 of t here is this function there, which is 0 from 0 till 1, and it is minus 2 from 1 till 3. So 0 multiplied with anything will result in 0. That's why we have reduced our integral from 1 till 3 instead of 0 till 3. So effectively 1 till 3 will have some values to be solved under the multiplication product of these 2 functions, right? So for the remaining time period of 1 till 3, S1 of t is this function minus 2, and here it is written minus 2, and phi naught of t is 2 over under root 12. Here it is written, right? So all you have to do is to solve this equation. Right, so in this step I have graphically solved this equation, and I've put everything on the slides again for you. You may do it in some other way that suits you, but this is very expressive way of solving it and very detailed way of going about it. So I have put it in the slides for you, so you can see it in your free time, how I have graphically solved the problem. All I have to do is to represent the signals graphically and adding them and subtracting them accordingly as per the equation requirement. Alright. So what I got in the end is phi 1 of t, which is nothing but the function g of t divided by the norm of the function g of t, which is g of t divided by under root of eg1. Once I have obtained g1 of t in the previous step, you can graphically see it. You can solve for its energy. You can compute its energy by taking the square of the function and then integrating it. So from 0 till 1 it is 4 by 3 square, and from 1 till 3 it is minus 2 by 3 square. So you can compute the energy, which is equivalent to 24 by 9 here. And you have to compute the norm of the energy, that is, you need to take the under root of the energy in the next step and substitute it there in this equation. So as a result, you get phi1 of t, which is equivalent to under root of 3 by 8 times g1 of t. Now since you know what is g1 of t, you can easily multiply the amplitudes of g1 of t with under root 3 by 8, and you end up getting this function there, which is your second basis function, graphically represented here. Now you proceed towards the third step. Since you have tested and chosen S0 of t in the first step, S1 of t in the second step, and now you are left with these two functions to be chosen in the next step. Right, so you selected function S2 of t in the third step, and you would like to subtract the contributions or projections of S2 of t onto basis function phi naught of t and the basis function phi1 of t. Since you have already calculated the two basis functions in the previous steps, phi naught of t and phi1 of t, so you have to subtract the projections of S2 of t that were there on the basis function phi naught and the phi1 in the third step. And again you have to solve the equations mathematically, as well as you might want to visualize them graphically. Whatever is the easy way around for you, you adopt it, right? So if you substitute the function values, you end up getting the reduced form of the equation here, and finally some graphical illustration again to get the result. And it turned out that g of t comes out to be 0. If you visualize these three functions graphically, S2 of t minus 2 over under root 3 phi naught of t minus under root of 8 over 3 phi1 of t, if you graphically visualize them individually and add them together as per this equation requirement, so you end up getting 0 as a result. And as I told you, if you get 0 as a result, this means that no new basis function is added into your basis function set. That is, in this step we are not going to produce any basis function. So we go to the next step, and the next step was to choose the remaining function, if any available. So we have to go for this function in the final step. It was left to be selected. So we go for the final step. Let g3 of t is equivalent to S3 of t minus the projection of S3 of t onto the previously calculated basis functions. The previously calculated basis functions were phi naught of t, this one, and phi1 of t, this one. There was no phi2 of t because in the third step we didn't come up with any new basis function, right? So we only need to subtract the projections of S3 of t onto the previously calculated basis functions, which are phi naught of t and phi1 of t. So if you solve this in the same manner like we did for the previous cases, we end up getting this reduced form. And in your free time you can follow these equations and the calculations I've done there for you, you will end up getting this reduced form. And in the next step you can visualize it again. Since it's a reduced form, you can easily visualize it. You can plot S3 of t and then subtract the remaining portion out of S3 of t in the next step. This is your S3 of t and that's the remaining portion plotted here. And if you subtract them, you end up getting this function g3 of t. And as a rule, you have to compute the norm of g of 3 and divide g of 3 by its norm to get the basis function out of it. Now this result is non-zero, right? So this means we can have a new basis function out of this process. So phi2 of t is under root of 3 over divided by 8 times g3 of t, and this is your basis function, the final basis function, right? How did you compute EG3 of t? This is done here in this rough work there. You can follow this rough work here to compute the value of EG3 of 3, which comes out to be under root of 3 by 8, right? So this is the last basis function that we have computed. We have three basis functions, phi naught, phi 1 and phi 2. The signal space dimension comes out to be 3 as a result. So this means our constellation diagram has to be three-dimensional in nature. Difficult to visualize the signals over there, but you can use any software to visualize your signals onto three-dimensional plot. Now let's try to represent our signals S1, S2 and S3, S4, S0, S1, S2 and S3 using the basis functions that we have calculated, the three basis functions. So we are able to reduce the complexity slightly. Like earlier we had 4 signals, but now those 4 signals are going to be represented using only 3 basis functions. So previously we were required to have 4 match filtered branches at the receiver end, but now they are reduced to only 3, right? So we have slightly reduced the complexity of the match filter. So let's see how we can formally come up with the representation of signals in terms of the basis function in the last step. That is, we would like to see how much of the signal component that is associated with the basis function phi naught and how much of the signal component that is associated with the basis functions phi 1 and phi 2 respectively. That is, we are trying to find out AI of J's, AIJs. Right, so this is the equation that is used to represent the signal in terms of the basis functions along with their contributions. We have capital N equivalent to 3 in our case and capital M equivalent to 4 in this example. So if you expand this equation, it will expand for capital N equivalent to 3, means we are going to have 3 functions as a result being added together to obtain one function here. For example, if you substitute I is equivalent to 1 here, you can see this is how the summation is going to expand for I is equivalent to 1. A11 is nothing, A1 naught is nothing but this function here in the brackets. A11 is here, A12 is here. You see, we have used the variable a with the subscripts I and j. So if you substitute I equivalent to 1, j will vary from 1 till 3, since we have 3 basis functions. So it will end up getting a11 times psi of 1 of t plus a12 psi of 2 of t and a13 psi of 3 of t. So this term there is a10, this one is a11, this one is a12. Alright. Actually this should have been started from j equivalent to 0 till 2. Here the index starts from 1 till 3. It is the same thing actually. The index should have been written 0 till n minus 1, capital N minus 1. The point is we have 3 basis functions and this summation will result in getting the 3 terms out of it. And similarly we can expand S2 of t and S3 of t and S0 of t. S0 of t expanded result is not mentioned here. However, I have computed the end result of S0 of t for you because S0 of t was very simple to express. You can see here S0 of t is equivalent to under root E naught times theta naught of t. In other words, S0 of t is equivalent to under root 12 times theta naught of t. If you substitute under root 12 there on the left side, S0 of t becomes under root 12 times theta naught of t. Right? So that's why I have written it directly here, under root 12 times theta naught of t. If you solve these integrals, you will come up with the answers, right? And you will see how much of phi naught of t is present in S2 of t and how much of phi 1 of t is present in S2 of t, etc., etc. and so on for all of the other signals. In other words, I'm trying to say is you are calculating the contributions of these basis functions that are present in S1 of t, the main signal, right? It's like calculating the contributions of the unit vectors x, y, and z that contributes towards the main vector, right? So the same thing happens in signal space. Once you have calculated these contributions, you would be able to plot it on three-dimensional constellation diagram in which we have three axes, phi 1, phi 2, and phi 0. All are independent from each other, and you can plot the signals onto these axes depending upon the contributions that result out of these three equations. So I would like you to solve the above equations, right, and tell me the result and submit your results in the next class before I give you the lecture. All right. So I hope you understand the GSO process and how we can obtain the basis functions out of the GSO process in the first step, and then how you can represent the signals using the basis functions in the second step, and finally plot them on constellation diagram in the third step, right? There is another example in the slides. You can see this one is very simple again. You have three signals there, and you are asked to do the same series of steps to obtain the basis functions out of this example. You can go through it in your free time, and let me share the results with you. In this example, you are able to come up with two basis functions for the possible three signals, right? And you are able to represent those signals x1, x2, and x3 in terms of those basis functions. You are able to plot them on constellation diagram as well. Okay. So I hope this was not that difficult, and provided you solve the examples yourselves, I would like you guys to make notes and solve these examples again by your hand in order to understand how the things are there in the GSO process, and you would be feeling much comfortable afterwards. Unless you solve them yourselves, you won't be in a comfort zone. Alright, so next time when we meet, we would have an interactive session regarding the two lectures that I have shared for you, and we would like to move on to the next topic, which is also very important, the optimum design of the receiver structure. We would like to see how in the best possible manner we can recover our signal on the basis of conditional probabilities, right? All right, thank you.